And now after simulating the entire frame range and flipbooking the results, we have a shot that looks like this. And this is looking quite cool. Of course, we may want to really get in there and finesse things once we see the explosion in there with it, because we may want to adjust things in context. But overall, this is looking quite good, and I'm happy with this, so we can go ahead and start rendering that. So let's go back to our file cache here and just double check the attributes on this. And you can see we have lots of detail attributes with various bits of information about these volumes. And the key one that we really need to watch out for is this shop material path here. Because we've defined a look for this Shockwave volume on the look tab of our Pyro solver, which is essentially setting a material shader on this volume. And I'm going to ultimately render this in Redshift. So if we leave this shop material path on there, then that may mess up our Redshift material assignment later. So I'm going to make sure to delete that. So I'll drop in an attribute rename. And the only attribute that we really care about keeping in here is the name attribute, which is going to store the name of each of these volumes. So on the primitive tab of our attribute rename, under keep attributes, I'll just change this to name. So that's all cleaned up there. And on the detail tab, I'm just going to remove the asterisk under keep attributes because we can clean up all of that stuff as well, even though it's probably harmless. And if you really want to be obsessively clean, we also don't need that Pyro group. So I'll drop in a group delete as well, put in a star to delete all groups. So now we have this super clean output that's ready for rendering. All we have is position and the names of the volumes and the volumes themselves. So I'll drop in a null here, call this render shockwave, and then we can go ahead and start setting up the Redshift render for this. So let's jump up to the object context and then create a new geometry object to render that shockwave. So create a new geometry, call it render shockwave. I'll set that red like usual. And then dive inside here and drop in an object merge, then point this to object/shockwave/render shockwave. And you can see this is correctly bringing in our volume here. This has density information and velocity X, Y, and Z volumes. And it's pretty important for these volumes to be set up as separate velocity X, Y, Z volumes like this. Sometimes you'll see velocity information stored in a VDB singular vector volume, and I don't believe that works properly with Redshift. So make sure that you do see this vel X, vel Y, and vel Z, not just a single vel volume with vector information. And just to illustrate this problem, we can merge those volumes together. And right now these are native Houdini volumes. You could try caching out VDBs instead. That could potentially be more efficient on disk space and such. So if we go back to our Shockwave setup here on the Pyro solver, if you look at the export tab here, there's this convert to VDB option so that you can make sure that you're saving VDBs to disk instead of Houdini native volumes. And I'm not going to bother with that right now, but it could potentially be better in terms of disk space and such. So going back to our render object here, just to show you what that vector velocity field might look like on a VDB, let's first convert these volumes to VDB volumes, and then on this convert VDB, set convert to VDB. So now you can see it's listing 4 VDBs here instead of 4 native volumes. And even though we've converted this to VDBs, we do still have velocity X, Y, and Z grids. However, in some cases you might wind up with a vector field instead. So to show you what that looks like, let's drop in a VDB vector merge and display that. And this will automatically find volumes with the same name ending in .x, .y, and .z. So you can see now, instead of those 3 volumes, now we have a single velocity volume here with that vector information. So I don't believe this will work properly in Redshift, So if you do see a volume like that, you may need to do a VDB vector split. So if you drop in that VDB vector split node, you don't really need to change any options here. And if you display that, this has now converted that vector field into individual velocity x, y, and z volumes once again. If you did have multiple vector volumes in here and you didn't want to change all of them and you only wanted to change velocity, you could also, on the VDB vector split under the group here, pick a specific volume that you want to split up into its components. So I'll select velocity there. And you can see our results are the same, but if we had other vector volumes, then those ones would not be split because we've just specifically selected the velocity volume here. But in any case, I'm just going to leave this as it is once we object merge these volumes in here and render those directly. So let's jump out of this geometry object, go to our Redshift object tab here, and then go to the volume tab. And to enable that velocity information for motion blur, you can turn on this use velocity grids option. And as we've discussed, you can see this is expecting those 3 individual fields there for X, Y, and Z. And we can also turn off the display flag on this render object here because we don't really need to see that all the time. And let's make sure that we have some lights that are affecting volumes. So it's very important to turn this option on some of your Redshift lights. So if we go to our main RS light dome and scroll down, you can see there's this volume contribution scale that's been turned up to 1. And we can make sure that the lights from the creatures are also turned on to contribute to volume rendering as well. And sure enough, our light for the creatures and the no viz version of that are all properly set to light up the volumes as well. When you drop in a Redshift light, this isn't set by default. So if we create a new one here, go to the light tab and scroll down, you can see the volume contribution scale is defaulting to 0. So you're not going to see your volumes lit properly. I think they might not show up at all. So it's very important to make sure that your lights in the scene are affecting your volumes. And now let's set up our shader. So let's go to the material context, drop in an RS material builder, and call this RS Shockwave, and dive inside there. And inside here you'll see that by default that RS material builder just has a standard surface shader on here, so we can just delete that material. And instead we're going to drop in an RS volume and connect that to the volume input of the Redshift material. And we'll come back to adjusting some of these material properties once we get some initial renders going. So let's go back to our object context, and then on this render shockwave object here, let's set the material path. So that'll be mat/rs_shockwave. And now over to the out context to set up the Redshift drop. Drop in that Redshift render. And for this one, I'm not working on the wide shot. I have a close-up camera setup for the explosion shot here. Just another kind of standard turntable rotating around this creature on the ground as it's exploding. So I will call this ROP explode-pyro. And ultimately I'm going to add the fire and explosion into the same render as the shockwave here. But for now we're just dealing with the shockwave itself. So on this Redshift ROP, let's point this to the correct camera, which is master cam explode. Under objects, let's get rid of the star under candidate objects. And for force objects, we're of course going to pick our render shockwave. I'm also going to render the creature on the ground for now, and the environment, just so that we can see this all in context. However, instead of bringing in the entire renderable environment, we can just bring in the section without all of the fractured destruction detail. So if we go back to our render object for the environment here and dive inside there, we zoom out a bit and look at all of this destruction detail that's being brought into this renderable environment. That's going to be a lot of extra geometry that we don't really need in our explosion shot. So it's a good idea to kind of be smart about what you're including in the different shots in your scene. So it might work just fine to include all of this heavier geometry when we're rendering the explosion close-up, but just to optimize things a bit, I'm going to make a copy of my environment here, paste in that copy, and I'll call this one Render ENV No Fracture. And we'll leave everything the same on this render object, but dive inside there. And in this one, I'm just going to delete out this destruction geometry, that is the RBD simulated portion here. And I'm still going to leave in this static region of the fracture and the base of the terrain, which is all we really need if we look through the close-up camera for this explosion shot. All the other destruction stuff is not in frame here. So that can certainly speed things up a bit. So now back to our out context and the explode pyro ROP here. I will also include that render ENV no fracture in my rendered object list, and then also get rid of the star under candidate lights. And for the force lights, we'll select the RS light dome and the RS light creatures no viz. So now let's open up our render view pane, select the explode pyro ROP, and let's go to a frame where we know we have a decent portion of the shockwave visible. Let's see what 85 looks like and start that IPR render. And now our scene is rendering correctly. One small problem we're seeing is that this creature here doesn't have its material showing up properly. Ultimately, we're just going to be rendering the pyro stuff without the creatures and the geometry visible, but I'll still double check and fix this. So going back to our render object, it looks like we've included the creature ground object, which is actually not meant to be a render object. We shouldn't be using that one. We should be using the render creatures object. And now after fixing that, that's looking a lot better, and we can start dialing in the look of the shockwave here. Let's also turn off the display of the light dome texture there. So going back to our light dome, and then scrolling down to this enable background parameter, let's turn that off and re-render. And that's looking better as well. Now let's jump over to the shader on the object to dial in the look of our shockwave a bit. Let's dive inside there and select that volume 1 shader. Now the main things that we're interested in for rendering a volume like this are the scatter and the absorption. So the scatter is essentially like the diffuse color of the volume. The absorption is essentially the transparency of it. So the scatter coefficient will make it brighter or darker overall. So if we turn that down to 0.5, we can see what that looks like. And perhaps I'll turn on the render region option. So let's rerun this render with the scatter coefficient turned down. And you can see that turning that down makes this a bit darker. So we can tweak that scatter coefficient to control the brightness and darkness of this. And we can also tint this as well. And I like to tint this shockwave so that it's similar to the color of the terrain. So let's go over to our environment shader, go into RS ENV, then go into the color constant that we're using for our base color, and I'll copy that parameter, go back to our shockwave, and you can either paste a relative reference or the raw values into the scatter tint here. So I'll just paste in those values, turn the scatter coefficient back up, and see what this looks like. So now our shockwave is based on a similar color as the terrain. It's looking a bit dense right now and a bit thick, so let's turn down our absorption coefficient to make that a bit more transparent. And now I think this more transparent version of the shockwave will probably work a bit better. Now, in addition to controlling the look with our scatter and absorption values, we can also remap the density on the Advanced tab here. So if we want to dial down the density of this overall, we can set a new range here. So if it's ramped from 0 to 1 and the input, we can remap that from 0 to, for example, 0.3, and then render this again. And now with that lower density on the remap, it's looking a bit too transparent. So I'm just going to dial up the absorption a bit. turn that up to 0.8. So that's looking a little bit better. Let's try turning up the brightness a bit more on that scatter coefficient. This is looking pretty cool, and we can start rendering this in motion. So let's go back to the out context and back to our Explode Pyro Redshift ROP. And instead of rendering the environments and the creatures along with the shockwave, we generally want to render these as matte objects, so they're just holdouts. And previously, we had discussed some things you need to watch out for with how matte objects work. So if we currently re-render this, then you can see this doesn't look any different. The matte objects are still visible in the render. And this is why we use this matte parameters from reference. And we've already set up a matte parameters reference at the object level here. If we take another look at that, you can see we have this matte parameters geometry object. It has matte enabled and the alpha set to 0. So going back to the Redshift ROP, we'll set the matte parameters from and point that to our matte parameters object and render again. And now you can see our holdouts are working correctly. And the alpha channel looks all good as well. And of course, we're still just rendering one region of interest here, so the rest of the image doesn't look right just yet. And now before kicking off a test render of this, let's check a few more things. On the Redshift tab, I'm going to leave this on automatic sampling, which should give us some fairly high quality. And on the Motion Blur tab, let's enable this and turn on both Deformation Blur and Instances/Particle Blur. Under Globals, I don't think we need to mess with any of this stuff right now. Under Global Illumination, I've been just setting both primary and secondary GI engine to brute force. And the other stuff we can leave alone. Under Output, let's set a proper path for this render. So I'll set the path to hip/render/pyro-hipname for the directory, and then pyro-hipname for the file names as well. We can get rid of the $OS, which just refers to the name of the current node, in this case Explode Pyro. And it can be nice to include the hip name in your render paths here, because that can help you to keep track of the original files that generated these renders. So let's do one last quick test of the full frame to make sure everything looks right before kicking off a render of our full frame range. And this looks all good. Alpha looks correct as well. So I'll set this to render the frame range. In this case, I've set up the close-up shot from frame 75 to 240, and then render to disk. And now after rendering the full frame range, we have a result that looks like this. And this looks like it's working quite well. Everything's looking nice. Of course, to really assess this and perhaps finesse it a bit, we'll need to see it in context with the geometry renders in this scene and the explosion element as well. So if we take a look at this finished and composited explosion shot, you can see how that all comes together, and this shockwave blends nicely with the explosion to really sell the realism and impact of that event. For this version of the Shockwave Sim, I turned up the timescale a little bit. This is, I think, maybe a timescale of 2, and either version is working pretty well. This slightly faster one versus this version with the default timescale, so it's up to you if you want to play around with that option a bit as well. But either of those variations on that sim should work quite well with this explosion.